We are very happy to have Quoc Ho from ISD Austria talking about factorization, homology, and arithmetic of configuration spaces, I guess.
Yeah, thank you very much for the invitation. So I guess I'm going to start with some motivation. Okay, so I will start with some arithmetic motivation. So arithmetic, what I mean is that I guess there are two aspects. There's something called number field. So I'm aware that this is a topology seminar, so don't worry, this will be very minimal. So here's the observation. So if you take the limit when n go to infinity of the number of integers from say 0 to n, maybe for safety, it's very one to n, doesn't really matter. The square free over all integers from 1 to n, so over n. It's a classical theorem that this is zeta value, zeta 2 inverse. Okay, so for now I will refer to this. I wouldn't write formula like that, but I would say the density of square free integers among all integers. So that's what I mean. So there's a similar limit where you look at the density of pairs of relative prime among all pairs of, I guess, positive integers. So it looks very different what we are computing here, but somehow the result is the same. So it's also zeta 2 inverse. So you see that these two are somehow equal. And in fact, there's a generalization of both of these statements, namely the density. So for suffix m and n are just positive integers. Since that mn is greater than or equal to 2, then you can look at the density of, actually one quick question. How long is the talk? 1 hour, right?
Yes.
Okay. So the density, thank you. The density of n tuple of integers that are relative n prime. So we say that where it is shortly among all m tuples of integers is actually equal to zeta mn inverse. And so you will see that m and n can change, but as long as the product stays the same, then somehow all the results are the same. They're the same numbers. Right? People prove this, just do some counting and they realize this. So we call this sort of phenomenon coincidence in arithmetic statistics. Okay, so now that's the number field story. There's a parallel story in the function field story. So when it's a function field, I mean, we switch here and do, I guess, number theory on varieties defined over a finite field. So we have a bunch of equations, cut out some variety defined over, say, FQ somewhere. Right? So let X be a geometrically connected. So if you don't know what this is, doesn't matter, just some sort of connectedness variety over FQ of dimension D. So we should keep in mind the following dictionary. to translate the statement above to something about point counting on X, right? So when we're in X, so points on X, FQ points on X are essentially, are exactly solutions to these sets of equations that define X. So here's the dictionary. So points in X FQ, so elements in there should be thought of as prime numbers. And points in the symmetric power of X, FQ, should be thought of as corresponding to integers. Right? So this same thing is X to the, so union of all X to the N mod Sn. So now it starts to look more like a geometry or topology talk. Right, and then we can make the same statement. In fact, the following statement is true. So before, right, I said the word density, but when you actually implement it, you need to kind of pick an order and pick the limit using the order. Like the order was the size. Here, the order is going to be this n. So the same is that the density of conv dx fq in sim dx fq. So conv d is so it sits. It's an open subthing of sim d where you, where you disallow points to collide. Is now zeta x to the inverse. Right, so we recall that just to remind you. So zeta function in number theory is like 1 over 1 minus p to the negative s. And here you do something similar. This is like product over close points of x, and something similar, 1 minus something that look like this. Essentially some products that essentially taking over all the primes of x, all the points of x. Okay, so let's correspond to the first statement above, right? Square free should be thought of as things in here, and all integers should be thought of in here, and we compare how many of them relatively, and we get this also this zeta value. And then similarly, you can compute the similar density, the sim d1 times sim d2. So I would suppress x from now on, just to save time. And you look at the locus where the two things, or two factors are different, and then in just all sim. And then you actually also get zeta x to the inverse, right? So these two things are the same. Okay, great. Now let me state the ultimate generalization of these things in terms of point counting. But before doing that, let me start with the definition. Just to introduce these objects called generalized configuration spaces. So I'm sure everyone has seen it before, but maybe a slightly different notation to just make sure that we're on the same page. Okay, so again, let m and n be positive integers such that m times n is greater than equal to 2. Then for each d, which is an m tuple of numbers, m, then sim, I define sim d of x to be the product over all the I of sim di of x. And then I also define z d nx to be an open subthing inside x that consisting of all configurations. So I view these the factors in the I factor as having some color I. So this kind of a color version of symmetric power. So consisting of all configurations such that for each point x in X, right? So each point x in X may appear in one of these factors, and essentially I want so we're gonna have some multiplicity coming from here, and I want the multiplicity to be less than n for some color. So there is a color where the multiplicity at x is less than n. Okay, so at least for me, it sounds a bit confusing. So I will just give an example, and then hopefully it becomes clear. And before that, let me actually introduce one more notation, which is this. So I will denote ZMN to be the disjoint union of all the D. Okay, so let me give some example. Hopefully it's clear what I mean over here. Okay, the example is following. So first of all, let's look at Z. Okay, so I would just consider the case, say when M is equal to 1 right now. Right? So all tuples are just one tuple, just numbers. And then when N is infinity, right? Everything is smaller than infinity, so this condition over here is empty. So Z D infinity X is a symmetric power. Okay, great. And then when N is equal to 2, right? There's only one color to worry about, and we need that color to be always less than 2 to support. So this thing is just conf D X. Okay, so that's the case when M equal to 1. Case when M equal to 2, then any D is equal to D1 comma D2. And then the infinity case is also just the whole symmetric power. Let's consider the case where N is equal to 1. N equal to 1, that means that Z D1, D2, 1, X is precisely sim D1X times sim D2X and disjoint. So I hope now it's clear what I mean by this. Okay, so that's the number of arithmetic motivation. So last but not least, this is a topology talk. So here's the topological. So by the way, so this theorem above that I mentioned, this coincidence. Actually, I forgot to say something. I just defined things, but I haven't stated anything yet. So here's the statement. So same as that the density of ZDNX FQ in ZD infinity or same sim D is precisely zeta of x dmn inverse. And so you see that specializes to those two examples that I had earlier. So this theorem, the very classical that due to I think Minkowski. I think in the 80 or 70. Okay, so finally now the topological motivation. So the audience should actually know better than me. So this is actually some of this is going back to like Siegel, and I think like in the language of factorization homology, there's also Coopers and Mueller also prove this. So let's just focus on the case where x equal to R2. Then we know that the stable homology of of conv x, right, go to the stable homology of the double loop space of S2, whereas the stable homology of, so there's a D here, CMD1, CMD2x, disjoint, go to the double loop space of CP infinity, wedge with CP infinity. And these two are homotopy equivalents. And so somehow, it's also reflect kind of the same thing, where somehow this guy, so here you don't see any denominator because in R2, so sim has trivial. But you see that these two things are very different, but somehow at infinity, they are the same.
So did you picked X as R2 because there's this sort of circle that's kind of invisible when you loop it twice?
Okay, so actually I just picked it because I don't know what the statement is. Yeah, you probably know what a better way to say this.
Or just I think that there's in general there would be like a fiber sequence from like let's see which the S2, you know, like maps, compactly supported maps from X.
Yes.
S2 compactly supported maps into CP infinity, wedge CP infinity, and then the base is going to be compactly supported maps into S1.
Yes.
And so when you plug in X as R2, you get loops to S1, and if you know, S1's homotopy groups are concentrated in degree 0 and 1, so you loop it twice, yes, and it goes away. But if you like X is some higher genus surface, it would show up and it would like be the Jacobian. Like map from a surface into S1 is a like topologist version of the Jacobian, I think.
Yes. So essentially I also don't know how to say the denominant as a denominator. So all the arithmetic version, right, has some denominator, something over something, and I picked R2 because the denominator, they're gonna be just contractible space.
Yeah, so yeah, but it should. We get afterwards, but like
we should ask. Yeah,
it's all in like Siegel, in some sense.
Yes. Yeah. Yes. Okay, so very good. Okay, so so question. So this is Farb Wolfson Wood. They saw these things, and essentially they ask whether there is any relation between these parallels. That's all. Okay, so now let me say it more precisely. So namely, so because the statement in arithmetic statistics is some 7 at the limit, right? So first of all, then we expect that that's homological. So this space Z. So actually, before doing that, let me introduce a notation so that I don't have to see homology everywhere. So first some notation. So I will use A, MN to be the homology of Z and X. So homology, everything is joined in together. And then A, D, and X is the homology of the D part. Okay, so that's out of the way. So also for this talk, so say in the algebro-geometric setting, X can be anything really, but I would just restrict to X being smooth. So the reason is that when X is not smooth, you replace cohomology by Borel-Moore homology, and then everything will go through. And there's some shift that you have to take care of that is not very relevant, but confusing just because of the numbers involved. So in fact, smooth and compact. But otherwise, I mean, it works without these conditions. Okay, so here's what Farb Wolfson and Wood asked, that ZMN should should exhibit homological stability and second, all the coincidences above, maybe not the number theoretic one, but at least the function field and topology one, or the coincidence above has, I guess, cohomological origin. Okay. So they actually, this they proved. So for X smooth. And for this, they say that, so they don't actually say what homological origin means, but they essentially say that they prove that if we take limits of quotients of, say, Hodge-Levin polynomial, or maybe also Poincare polynomial, then we see the same coincidence. Right? Again, for X smooth. Okay, so so all these were done by explicitly calculating all the cohomology involved, or rather some spectral sequence, and then extract the Hodge-Levin polynomial and just take the division, and you see that it's somehow the same. So they pose the following question. Essentially, why do we actually see this? Like not just a calculation of coincidence, but like actually is a simple explanation for why there is such a thing. So one of the goals of today's talk is to explain. So today we explain how factorization homology answers this question. Okay. Very good. And then I would say something that might not have time to go back to, but in case I do actually have time, then there's also the following. So there's an enhancement of homological stability. That takes Sn action into account. So in the case of configuration space, then instead of taking unordered configuration spaces that, as I had earlier, you can also do unordered configuration spaces, and then those cohomology can have Sn action, and you can ask stability with respect to this action. So for ordered configuration spaces, this I think this was done by Ellenberg and Farb. Farb, I don't know. Maybe the order is, I meant to write in alphabetical order, but I think I failed. Okay, so I guess Church, Ellenberg, Farb. So they did that for configuration space. And then more recently, there's also this phenomenon that people discover that within the range where stability fails, there's a slightly better range where the failure of stability itself exhibits stability. So there's something called second stability. So I guess this is, so I guess in the homological setting, and for mapping class group, it's done by Galasius, Kupros, and Randall Williams. And then for representation for configuration spaces, also done by Miller and Wilson. And then for orbit configuration space, there's a recent work by Bibi and Gaddis. In fact, they also do something called higher representation stability. So I want to say that for generalized configuration spaces, one can also use Factorization homology to prove new higher stability phenomenon for generalized order configuration spaces. So probably I won't have time to talk about this, but essentially the idea is, so I mean the execution is somewhat technical, but the main ideas trace back to what I'm going to say now. Okay, so I think that's kind of the goal of what we're trying to do today. So now let me start with the actual content. So density and stability. So the real question is, how do we categorify quotient, right? So usually when you usually try to categorify something, right, by replacing, I don't know, like a number by vector space, right? Then what you usually do is that you end up categorifying addition and subtraction and not quotient. Right? So what we are doing is something multiplicative, which really suggestive that somehow factorization homology could be employed to somehow answer this question. So let me start with a very simple example. So okay, so from now on, I would denote lambda to be a field. So it's going to be the field or coefficient of my cohomology. For example, if I work in algebraic geometry, then I employ athletic cohomology. Or if I work in I don't know, topology, then I will use some rational homology. So it's like C or Q or Q or bar or whatever. And then here's the following example. So let A, in this case, is lambda itself. So again, everything I'm going to talk about is graded. So besides the cohomological grading, I also have an external grading. You consider this ring B, which is lambda, adjoint a variable U, where the degree of U is 1, but cohomological degree of U is also 0. Okay, so the first thing I want to look at is, so for a graded object, right, I can take the Euler characteristic, the graded one. So of B, and T is for the grading, equal to, so in dimension 0, in graded degree 0, I have one dimension, so that's 1. And then in graded degree 1, I have 1 times T, right? And then 1 times T squared, and so on. So that's 1 over 1 minus T. On the other hand, you can consider this. So I won't write, all my tensor are derived tensor. So it's implicit there. So you see that this is lambda in graded degree 0, direct sum with lambda in graded degree 1, but shifted by 1. So I use cohomological grading. Cohomo. So this thing lives in cohomological degree -1. So then I compute the graded of this guy with formal variable t. Then I see that this is 1, and then in degree 1 is in all cohomological degrees, so 1 minus t. So okay, so via this example, I just want to say that 1 over 1 minus t is inverse of 1 minus t. Right? So that's a very simple calculation. And from this, I want to say that we should view A tensor with B, sorry, A tensor with lambda over B as a categorification of something like A over B. Right? So this is how we can categorify a quotient. So whenever we see a quotient which has categorified, we should look for some algebra structure and do some relative tensor. Okay, very good. Okay, now, so this suggests that we want to equip A, M, and X. So we call that this is the cohomology of Z, M, and F, which is generalized configuration space with a commutative algebra structure. And then try to see coincidence at the level of relative tensor. Okay, so let me say it more precisely. So because our space X is connected, so note that H0 of A, M, N, S, X, right? So Z, M, and X, right, is a disjoint union of all these pieces. And each of these pieces is connected. So H0 just pick out the connected component. So this is lambda of X1 all the way to Xn, where degree of Xi is 1. Okay, so it's 0, 1, 0. This is in I, so I will know this is 1i. And cohomological degree 0. And this is the same for the infinity one as well. Okay. Okay, so that's the first thing. Second thing is that, so now, right, you can use these xi because these are, once you equip these AMN with a commutative algebra structure, then you can use these xi's to act on AMN. So that means that AI will send to A, B, right? So we can try to prove. So we can use this to witness homological stability. Right? Meaning that we can try to prove that this map exhibit homological stability. But even before doing that, we can actually do the following already. So we can take the co-limit for D go to infinity. Of this A, D, and X using this map. And now we use that to define this object. So this object, let me just abstract color co-limit, is defined regardless of whether you have homological stability, right? And so we want to prove. So by abstract nonsense, this limit also inherits the commutative algebra structure from the big guy, the AMN guy without the bar. And also all maps between them are also preserved. So we want to prove coincidence at the level of relative tensor of these guys. And then recover coincidences in, say, point counts or Hodge-Delin from this quotient, from this. Right? So we have all this and just somehow come up with a way to declarify it to get point count and to get quotient of Hodge-Delin polynomials. So here are the theorems. So obviously, some form of it is also proved by Farb Wolfson Wood, and then for non-smooth case, is the following. So you have A, D, and X with those map Xi has homological stability. And okay, with precise range. So I wouldn't say what the range is. And I also want to say that you can actually generalize this a bit. You can replace n by an n tuple and define an appropriate one. Then the theorem also satisfied. And then the next result is that, the main interest, at least for me, is that you have this guy. The isomorphic when n is equal to m prime and n prime. And you recover and can recover Hodge-Delin and other stuff from this statement. Okay, great. So those are the two results I want to explain how to use the Factorization homology to prove. So since this is the topology seminar, you're probably familiar with a slightly different formulation of Factorization homology compared to what I say right now. So what I say right now may seem a bit less geometric, but the reason is that I want to do something that works both in algebro-geometry and topology, so that I can recover point count and also Berry numbers and so on. So let me quickly explain what I mean by Factorization homology. So this subject started, has a long history. I guess not, depending on how you look at it, but so it started with Bellins and Drinfeld, and then Francis Gatesbury and Gatesbury-Lurie. So somehow they started with the algebro-geometric picture. And then somehow various people, I think maybe Lurie, realized that these things actually had this history. I guess the topological picture has history that went back to May or maybe other people, under the guise of EN algebras and stuff like that. So the kind of factorization homology that I'm going to talk about is kind of a simplified one. Namely, if you think about the counterpart in topology, then it just corresponds to factorization homology with coefficients in commutative algebra, not EN algebra. So it's a much simplified version, but that's enough for our purpose. Okay, so two main features that I care about that I use from factorization homology is that it's multiplicative rather than additive, like usual homology theory. And in the context of algebro-geometry over FQ, it has something called multiplicative trace formula. So we'll explain it shortly. So this is the thing that's responsible for the appearance of zeta values. Remember that we have this zeta value that has this infinite product expansion. Okay, so here's what I mean by factorization homology. So you start with x mapping to a point. So x can be either, essentially, if you have a nice enough sheaf theory with 6-functor formalism, then you can play this game. For me, my foremost interest is the algebro-geometric version. So I just take it as analytic sheaves and that sort of theory. But you can take constructible sheaves in topological setting as well. And then let me call this P. So the carrier of sheaves on a point is just vect. So by vect, I mean really the derived category of chain complexes and not just the abelian category. Okay, so everything I say will derive by default. Okay. So that's a functor. They go from vec to a point that you know by P upper strict. So if you haven't seen the strict functor before, then there's not much different from the star, because in our case, X is smooth, so upper strict and upper star differ by just some homological shift. But in general, it's something different, and that amounts to this Baromo homology that I talked about earlier. But in any case, for us, upper strict is just a shifted version of upper star. And this thing is monoidal, it's symmetric monoidal. So here I will pick a symmetric monoidal structure that I call strict, tensor strict. So essentially it's Verdier dual to the star one. So if you really want to think about the star one, I think not much is lost. It's mostly the kind of technical thing that I had to use this. But in any case, so you have this and this is upper strict. So if you had star here, right, you can use star monoidal structure instead. But I want the strict one. So this symmetric monoidal, so that induces corresponding functor between the categories of commutative algebras. Right, so because I work everything derived, so really on the for example, com algebra vect is a DG CDGA. And then by adjoint functor theorem, you know that there's a left adjoint. So we know that by pi, so P lower question mark. Right? Note that P lower question mark is different from the usual push forward. So the usual push forward is only left lax monoidal, so it doesn't induce a functor on the level of commutative algebra objects. So, but pi lower question mark exists for formal reason, and is something. And we don't actually use much. So just right off the bat, we can actually just abstract nonsense. We can show that pi lower question mark of sim v. Right. So if v is some sheaf on X, you can form the free commutative algebra by taking the direct sum of all the sim. This is same as sim of pi lower strict of v. Right. So pi lower strict preserves free object, so because left adjoint. Okay, so that's one thing. So this somehow you can kind of see how the multiplicativity of the functor pi lower question mark. The second remark is that because pi lower question mark is a left adjoint, it preserves push-outs. And note that push-out in the world of commutative algebra means relative tensor. In particular, P lower question mark, so of A, B, C is the same as P lower question mark of A. Right, so that suggests that whatever thing that we want to prove in the end about relative tensor, we try to prove it at the coefficient level already. And I forgot to say that this is what I mean by factorization homology. And again, it's only for commutative algebra coefficient objects, which is simpler than what topologists usually use when they actually deal with factorization homology. The next, I want to say some word about trace formula. So again, what about I'm saying now? I mean, you have to have some finiteness condition, right? Because I'm taking the trace of something, then I need something to be finite dimensional for it to even make sense. But that aside, then we can do the following. Okay, so before I say that, right? So this adjoint functor up there has a graded version as well. So namely, I can replace sheaf on X by z to the m graded and vect by z to the m graded. And then everything we go through just have this formal grading hanging around. So unless strictly necessary, I won't include this in any notation. But implicitly, everything is graded. Okay, so when you have a variety definable over a finite field, then it admits this action, Frobenius action, and all the cohomology also admit Frobenius action. And so when we do this game, there's the trace formula that one can prove. It has the following form. Right, so this is just to say that why this has anything to do with zeta value. Essentially, it's just by decolorizing using this trace. So I won't say much about this. I will say more about the cohomological aspects. Okay, very good.
Okay, is pi p?
Oh yes, sorry. Yes, so in my notes I had pi, and somehow I started talking, I used p, and then I got confused. Thank you. Yeah, so pi is equal to p everywhere. I think I got all of the instances. Thank you. Okay, so now the question is, what should we plug in to get AMNX? Right, we're really interested in the cohomology of these generalized configuration spaces. So what is the coefficient object that we should plug in? So it's particularly simple. So before doing that, let me introduce a very important functor, delta lower question mark. So there's a functor that goes from commutative algebra object from sheaf on X, right? Because so far, whatever that I said so far, right, doesn't look like there's any power of anything. Everything happening on X. So there should be a device that links that to configuration spaces. Okay, so really I should be talking about commutative algebra. So I haven't defined it for you, the monodal structure on this guy to take the commutative algebra object so that I can take commutative algebra objects in it. So it's defined by essentially taking union of configurations. And so I can do this, and then I can pull back along the diagonal. And by abstract nonsense, there's also a pull forward. Okay, so let me say, so this functor essentially exists by abstract nonsense, but one can actually say a bit about how it's constructed. So let me, so first let me ignore grading, and I will try to explain. Now I will explain how to get something on X squared from something that is commutative algebra object on just X. Right? So start with A, which is an object in here. So I will ignore grading. That means that has a multiplication structure, right? So it has A, tensor A, go to A, right? So that's part of the structure. So let me unwind it a bit further. So this is the same as A, block tensor with A, and then delta upper strict to, so this is something that lives on the square of X. So I strict pull back to the diagonal, I get something that lives on X. It's just in that object, which is this. And so I have a map from that to A. Okay. Or I can, but I'm really interested in objects that actually live on X squared. So let me push the whole thing to X again. And then by junction, I have a map like this. I can push out. And I get something I call A2, which is something that live on shift on X squared. Okay, so the geometric meaning of this construction is the following. So if I visualize X squared as this box, this is the diagonal, then all I'm constructing is that I use, so the fiber above a point on the complement of the diagonal, we have to form AX, tensor AY. But then on the diagonal, it's just AX. Right? And so the point is that I use the multiplication structure on A to glue A tensor with A on the complement diagonal and A on the diagonal. So that's the kind of the collision kind of thing that you see in topology, like the round space and that sort of business. Okay, so the key statement is the following. So the key statement is that the factorization homology of A can be realized. So this is a theorem. I think Matthew Bellingson, Greenfeld, and then Francis Gatesbury. It's not so Gatesbury, Lurie. Is that pi lower question mark of A be the same as cohomology with compact support, so the chain of Zm infinity x with coefficient in this delta thing. A. Right? So this is something that looks abstract. You cannot decompose into two steps. First, you put it on the symmetric power, and then you just take usual cohomology. That's the statement. And now comes the theorem. One essentially let's say which algebra I should plug in. Okay, so I have pi lower question mark. Sorry. Let A and n be the following commutative algebra: x1 all the way to xn, then mod out by the product x1 to xn to the power n. So I hide some K-twist and homological shift. So there's some shifts, some twists you have to plug in to get the correct thing. But in any case, the theorem says that you take the factorization homology with coefficient in this AMN, then you recover the cohomology of the generalized configuration space. Okay, very good. So now, so essentially, the only thing I want to say is that about this algebra is that this denominator over there essentially responsible for saying that, okay, now I set the least allowed locus to be 0. If you go through this kind of construction, the delta question mark construction, you see that this denominator is about setting, it's kind of just deleting the disallowed locus. So that's intuitively why it is there. And so now density is now become very simple. So you know that you do this again. So when I put infinity there, just polynomial algebra without any relation. You see that this is precisely this plus this in greater degree n, and shift by 1 minus 2 dmn, and then take twist by negative dmn. And so up to some regrading, you see that as long as mn stays the same, then the quotient is the same object. And then you take factorization homology of this quotient, you get the same thing, because factorization homology preserves quotient or push out. And I want to note that this dmn is responsible for the zeta value that appeared earlier. Okay, so now I have 1 minute. I just want to say one last thing is that how do we actually compute anything about this? Right? So far, everything is formal. I haven't done any computation. How do we actually say homological stability? I haven't even proved that. So the thing is by a causal duality. So I won't say much about it, but it's about equivalent. And the version that I used essentially due to Francis Gates' query, which is some equivalence of carry between commutative algebra and Coley algebra. So under some technical assumption, these two categories are the same, and there are functors between them. So from right to left is something called cohomological Chevrolet complex, so it's some sort of Lie cohomology. And from left to right, there's something called co-prime. So this co-prime thing also show up in, I guess, Galacias, Ronda William, and Cooper's. They call it the derived indecomposable. And the point is that co-chef has a natural filtration whose associated gradient is just sim. And for sim, you essentially, for sim of something, homological stability and that sort of question is very easily seen just by inspection. And then you use this filtration to transport whatever statement you have on sim on co-chef, and then you're done. And then one last word. So this is how you prove homological stability and kind of get a computational handle. And one last word about representation stability is that you can try to develop kind of similar theory, but now for twisted commutative algebra, and you can think of twisted commutative factorization homology, and then you can run the whole game and you can get similar result, except that now the computation of co-shape and co-prime become much more complicated because these are, you can, for example, free Lie algebra in the twisted setting is very complicated. And so that's why a lot of results in representation stability is much harder to establish compared to homological stability. But yeah, so that's, I guess that's all I wanted to say.
Thank you very much. Are there any questions? I myself have some conceptual questions. Could you explain more, first of all, why this tensor is a categorification of the quotient again, and how it's related to density?
Okay, sure. So, right. So, our original goal, right, was to understand something that come out of Zm and X. So I will put like over Zm infinity X, where the curly thing is to denote either you do point counting or taking Hodgkin polynomial. We want to be able to have an object, some chain complex, so that we can decategorify and actually get these concrete polynomials or point count. So that was the goal. So that's the first thing. And then the second thing I want to say is that suppose you have suppose you have the following diagram, A, B. So suppose you have A. Suppose you have B is an A algebra and A is augmented, and you want to compute. So everything is graded, say. You want to compute this relative tensor. And with correct finiteness situation, finiteness condition, then one can show that when you decategorify this, you can prove that this is the same as B over A. So I guess your question is why this is true, right?
Yes.
Yes, very good. So this is actually via Koszul duality. So suppose, okay, so here's the thing. So via Koszul duality, the co-prime. So let me let A, B denote the Koszul dual of A and B. So these are Lie algebra, or rather co-Lie coalgebra. And Koszul duality is an equivalence of catalysts. In particular, it preserves push out. And co-limits of co-Lie coalgebra, when you only care about the underlying chain complex, is just taking the cone. So that's the first thing. So you know that the cone, right, categorifies difference. And now you go back, you do this and you go back, you see that up to some filtration, right, the co-shape, which is sim, and sim of a difference, I mean, it's some sort of exponential thing. Sim of a difference gives you a quotient.
I see.
So it boils down to like essentially sim of V plus W is like sim V tensor with sim W. But you have to go through this because you have non-free stuff and then you have to say something more, but it boils down to just that. Does that answer the question?
I see. I have another basic question, but let me see. Any other question from the audience?
I had a question. I mean, I sort of lost the thread a little bit, but so when I think about configuration spaces and factorization homology,
Yes.
and especially like indecomposables, I would have
Yes.
thought that you'd be working with sort of EN algebras.
Oh, yes. Okay, cool.
Commutative algebras, is there?
Yes. So I think one of the things that you prove with Cooper's is the following statement that so free. So this is, I guess this one went back further, but free EN and final homology of that is homology of, I guess, configuration space. And then there's another causality, E2 causality. E2, sorry, EN causality of free. By a point, I guess. Let me work linearly, so I won't say something stupid. So causality exchanges free and trivial object, so that's why you get this thing. So so the thing is that the free EN algebra has the natural structure of a co-commutative algebra as well. And so when you take causal dual and also linear dual somewhere, you land inside EN algebra of commutative algebra, and then do an additivity or something like that. This is same as commutative algebra. So that's how this algebra shows up. So it's the E2 causal dual of the free EN algebra. And then in the case of like symmetric, like two factors that are disjoint, I think you prove with Cooper's that something like N, U as an EN, EN algebra, you do this. Somehow E2 causal turns this kind of wedge thing into this relation xy equal to 0. So essentially, so this one I don't know. I don't actually know how to prove that this is that, but in general, causality just turn kind of free construction into a trivial thing. So give you an extra relation. So that's how you see commutative algebra showing up via this Lund additivity thing. Does it answer the question, hopefully?
I think so. And so like there's sort of 1x in the C of x mod x squared that's not 0, and that's like the EN cell.
Yes.
Oh wait, and maybe, or I don't know. I'm not sure that I have the dictionary right, but
essentially just and free to trivial, and this is a trivial algebra. This is like trivial algebra generated by one element. So
okay,
usually I work like non-unitary, right? So the C there is really just for psychological purposes, but really I want to work, which is this guy. So it's just C, and with trivial multiplication structure.
Maybe let's stop the recording now.